Ever looked at a volcano and just seen, well, a giant, angry mountain? What if I told you that deep beneath its fiery temper, there might be a hidden ocean? No, this isn't a sci-fi movie plot. This is real, groundbreaking science, and it's completely changing how we see our planet. Let's rewind a bit. We all learn in school that the Earth is made of layers: the crust we live on, the gooey mantle, and the core. The mantle is mostly solid rock, but it's under immense heat and pressure. Think of it like super thick hot taffy that moves incredibly slowly over millions of years. This movement is what drives plate tectonics, causing earthquakes and creating volcanoes. So where does the water come in? You see, the Earth's water isn't just in oceans and rivers. A huge amount is locked up inside minerals deep within the mantle. Imagine a sponge. A dry sponge is just a sponge, but a wet sponge holds a lot of water within its structure. The minerals in the mantle can act a bit like that sponge. One mineral in particular, called ringwoodite, is a super sponge. It can hold a surprising amount of water, not as liquid, but chemically bound within its crystal structure as hydroxide ions. Think of it like H2O getting split up and woven into the very fabric of the rock. For a long time, scientists have suspected there's a massive water reservoir in the mantle, specifically in a layer called the transition zone, which is about 410 to 1660 kilometers deep. That's way deeper than any human has ever drilled. We were talking about a hidden ocean that could potentially contain 3 times more water than all the surface oceans combined. It's a mind-boggling amount of water, all trapped inside these rocks. So, how do we know it's there if we can't dig that deep? This is where earthquakes come in. Earthquakes are not just destructive. They're also like a giant ultrasound for the planet. When an earthquake happens, it sends seismic waves, shock waves, rippling through the Earth's interior. Scientists have listening stations all over the globe that record these waves. The speed of these waves changes depending on the material they travel through. They move at one speed through dry rock and a different, slightly slower speed through wet, hydrated rock. By analyzing the travel times of these waves from thousands of earthquakes, scientists can create a map of the Earth's insides, and for years, the data has been hinting that the transition zone slows down these waves, suggesting the presence of all that water-rich ringwoodite. It was a solid theory, but they lacked direct physical proof. This is where our volcano comes into the picture. Meet the submarine volcano, Axial Seamount. It's an underwater volcano located off the coast of Oregon. It's one of the most active and well-studied volcanoes on the planet. In 2011, scientists predicted it would erupt within a few years. And they were right. It erupted in 2015. During this period of inflation, as magma was filling up the chamber beneath the volcano, something strange happened. The seismic sensors placed around the volcano detected a series of very unusual, low-frequency earthquakes. These weren't the sharp, jarring quakes we usually associate with eruptions. They were more like slow, deep rumbles. A team of scientists, led by an expert from the University of New Mexico, decided to investigate these weird signals. They used a cutting-edge technique called magnetotellurics, or MT for short. It's a bit complex, but think of it this way. Earth has a natural magnetic field, and it's constantly being bathed in electromagnetic energy from the sun and lightning storms. The MT method uses sensors to measure how these electric and magnetic fields penetrate the ground. Just like seismic waves, these electromagnetic signals behave differently depending on what they pass through. Materials that conduct electricity well, like salty water or molten rock, will alter the signals in a specific way. Dry solid rock, which is a poor conductor, will affect them differently. So by planting dozens of these sensors on the seafloor around Axial Seamount and listening for over a year, they could create a 3D image of the electrical conductivity beneath the volcano. And what they found was astonishing. Beneath the volcano's main magma chamber, about 30 kilometers down, was a massive area that was far more electrically conductive than the surrounding mantle rock. It was huge, stretching across a vast area. At first they thought it might just be a giant pool of magma, but the seismic data didn't quite fit. a chamber of pure molten rock that large should have slowed down the seismic waves much more dramatically than what was observed. This is where the two sets of data, the seismic and the MT, came together beautifully. The electrical data said, "There's something superconductive down there," and the seismic data said, "But it's not all melted rock." The only thing that could explain both observations was a massive reservoir of molten rock that was incredibly rich in water. We're not talking about a little bit of moisture. The models suggest the magma in this hidden reservoir could be up to 10% water by weight. That's an enormous amount. This water-rich melt, or hydrous melt, is highly conductive, explaining the MT data. But because it's still mixed with a lot of solid rock crystals like a slushy, it doesn't slow down seismic waves as much as a purely liquid chamber would, which explains the seismic data. Everything clicked into place. So, what does this all mean? First, it is the most direct evidence we have for a process that scientists have long theorized: water from the deep mantle feeding into the systems that create volcanoes. This hidden ocean isn't just sitting there. It's actively participating in the planet's geology. It is like we've found the main water pipe connecting the deep Earth to the surface. This discovery could also revolutionize how we predict volcanic eruptions. The amount of water in magma is a critical factor in how explosive an eruption will be. Think of shaking a can of soda. A regular soda will fizz a bit when you open it, but a soda that's been supercarbonated and shaken will explode. Water in magma acts like those carbonation bubbles. As the magma rises to the surface, the pressure drops, and the dissolved water turns into steam, expanding violently. The more water, the bigger the boom. By understanding the size and nature of these deep water sources, we might be able to better forecast the intensity of future eruptions, not just at Axial Seamount, but at volcanoes worldwide. This gives us a new tool, a new variable to plug into our eruption models, which could ultimately save lives and property. Furthermore, this discovery ties into the grand story of our planet's water cycle. We often think of the water cycle as evaporation, clouds, rain, and rivers. But there's a much bigger, slower cycle happening on a geological timescale. Water gets dragged down into the mantle at subduction zones, where one tectonic plate slides beneath another. It gets locked in minerals, stored in the transition zone for millions of years, and then, as we've just seen, it can come back up through volcanoes. This deep water cycle is crucial for life on Earth. It helps lubricate plate tectonics and it moderates the amount of water on the surface. Without this deep reservoir acting as a buffer, all of Earth's water might have been on the surface, or all of it might have been trapped in the mantle. This discovery gives us a tangible glimpse into the engine room of this planetary plumbing system. So the next time you see a picture of a volcano, remember what might be hiding beneath. It's not just a mountain of fire and ash. Deep down there could be a vast, hidden reservoir of water, a remnant of the planet's formation, slowly feeding the geological engine that shapes our world. It's a reminder that there are still incredible secrets buried right beneath our feet, waiting to be discovered. Thanks so much for joining me on this deep dive into our planet's hidden ocean. If you found this as fascinating as I did, make sure to hit that like button, subscribe for more science adventures, and ring that notification bell so you never miss an update. See you in the next video.